Coming up on this episode of the IoT Inc. Business Show.
So the trade-offs are computing things fast as opposed to the most accurate. When you have the luxury of more time, you will compute longer because it's a nonlinear trade-off typically in accuracy versus time. At some point, you need much more time to get a little more accuracy. And so when you're doing real time, then you make that trade-off with less accuracy but less time.
Okay, well, get ready for it. We're going to get down and dirty with predictive analytics. And when I say dirty, I mean mathematics of different forms of predictive models dirty. Geek fest? Yeah. But close your eyes and extrapolate how predictive analytics can be applied to your situation. By understanding how it works, you'll also understand the limits of what it can and cannot do. In this episode of the IoT Business Show, I deep dive with Anil Gandhi and emerge with a better understanding of predictive analytics and how it really relates to real-time and descriptive analytics.
All this and more on this episode of the IoT Inc. Business Show. The people, the business, and the technology of the next generation internet. This is the IoT Inc. Business Show. And now, here's your host, Bruce Sinclair.
Hello and welcome to the IoT Inc. Business Show. This show is for business leaders and managers employing the Internet of Things for their business or the business of their customers. I'm your host, Bruce Sinclair, and I interview the industry's leading authorities to find out how they use IoT to improve business and create value. If you like this show, subscribe to it on iTunes and go to iotinc.com to check out my complimentary articles, videos, meetups, and webinars. This is the fifth in a series of 7 episodes on analytics. Why? Because it's that important. Now, although this show is named the IoT Business Show, we haven't been talking a lot of business. In fact, we've been talking a lot more technology. Hang on, we're still going to continue doing technology for a little while longer. You know, I believe that if you want to put the Internet of Things to work, you have to understand how it works. Not enough to implement it, but enough to at least ask the right questions and budget for it. So, before we get into the business, we're still going to go into the technology for a little while longer. So if you're enjoying the tech, there's more of it coming. If you're wondering where the business is, it's coming. It's coming. If you'd like some help in planning your IoT business and product line, contact me. It's what I love to do. In addition to teaching at conferences, I also advise companies on the planning work that needs to be done before they get into the tech and start building their connected product. And on the sell side, I also advise IoT vendors. With me today on episode 26 is Anil Gandhi. Anil is a data scientist and president of Qualicent Analytics. He has 25 years of experience in semiconductor and electronic systems, where he's used advanced analytics and industrial IoT signals to make technical, financial, and productivity breakthroughs. Anil, welcome.
Thank you, Bruce.
So, Anil, what has been occupying the majority of your day today?
Well, data analytics is what I do, so...
Is that what you've been doing today?
Yeah.
Yeah.
A lot of numbers.
So when you say numbers, so what's your typical, like, what are you actually doing? Are you doing are you doing all the preparatory, like, what percentage of your time are you spending on the preparation of that data versus the actual crunching of that data, or actually then the analytics of that data?
Yeah, that's an interesting question, because people usually think of analytics as a lot of inspiration, but most of it is actually perspiration, which is data preparation and slicing and dicing and all of that. Yeah. And the inspiration portion of it, where you're interpreting the data results, that is a small portion of it, albeit the most important portion of it.
Yeah. Well, I mean, a lot of people reckon it back to the data warehousing days when, EDL was a big part of it. And I guess to a certain extent for a lot of IoT, EDL still is, I guess, a big part of it, right?
It is, yes. So it's It's just that the amount of data is much more massive, and so the kind of things or kind of techniques we would use today are different, more advanced, a lot more advanced, and we'll probably get into that today.
Yeah, we certainly will. Well, so before we get into that, why don't you tell our audience a little bit about yourself and your background in IoT?
Yeah. So I worked in the semiconductor industry and electronics industry for over 2 decades. In fact, over 24 years now, more precisely. So I work in the fab, or the factory as it's called also, semiconductor fab.
Okay.
In fabless companies, semiconductor fabless companies that typically outsource their manufacturing to foundries. Foundries would be the factories again. And then I've also worked for semiconductor equipment manufacturers that supply the tools to the foundries or the factories.
Okay.
And some of their clients as well. So in many of these engagements, we're looking at essentially industrial IoT signals, or what is also known as FDC, or fault detection and classification.
Ah, okay.
This would be the terminology in the fabs and the semiconductor fabs. So semiconductor industry, as you know, is one of the most advanced in terms of the things that they collect or data acquisition, with a very large number of sensors that are embedded in the tools.
Okay. I didn't know that, actually.
Right. And they measure just about every conceivable process activity, power, pressure, gas flows, temperature, you name it.
Right.
And of course, there's lots of test data at the back end. That is to say, after the device is fabricated. So work with analytics for all this data, inline and end of line. So the end goals, of course, vary. It could be increasing the yield or productivity, or if it's in the automotive supply chain, then it could be reducing field DPPM. And so, and likewise in the medical devices or healthcare segment as well. So the different metrics. So I work with all of that, different metrics coming out of with data coming out of FDC systems or industrial IoT signals, if you like, or Industry 4.0, which is another word.
We'll get them all in there. Okay.
Yeah. And so all of that.
All right. And so in your experience in working in the semiconductor and electronic systems, this is where you were actually doing the analytics, and that's where you kind of honed your craft, is working with that data?
Yes. So at this point, we're addressing the automotive and medical devices sector and the healthcare sector in general as well at Qualicent. And both of these sectors have very similar risk profiles. And so there's a commonality there that we can address in the same way. And both of these, so with the implication of this is that, or not so much the implication, but the reason they have a similar risk profile is that in terms of the cost of product failure, the cost of product failure is very high in both of these segments. Whether you measure it in terms of death or injury, or in dollar cost terms like regulatory, punitive fines, or reputational cost, and so forth. So in both of these sectors, automotive and medical, you can't afford to have field failures. And you see that in the automotive sector in the news all the time, the GM failure and recalls, so
or worse.
Exactly. So if you add up all those numbers, they're all in the public domain. It's a really massive amount, and especially when you add the reputational cost, the loss of sales and so forth, is really a massive amount. So we're addressing these two sectors because our analytic solutions are particularly suited to detect marginalities that cause these field failures. And I'm happy to talk about these marginalities also at some point in the conversation. But all of that is analytics, essentially. And a lot of the data that's coming out of the industrial IoT signals that we analyze.
Okay, all right. So you have a pretty solid background then. Tell us something though that most people don't know about you.
Well, I don't know if I would say they don't know about me, but I'm a numbers guy.
I think that's pretty obvious, isn't it?
Yeah. Let me put it this way. If it can't be quantified, it did not happen. Okay. So basically, I'm a quant.
You're a quant. Oh, I didn't know there was a name for that. As opposed to a qual?
There you go. So I didn't know that.
All right, quant. Let's talk about predictive analytics. I'd like to start there because as we've gone through in our show, we've talked at a higher level, on the different types of IoT analytics. Of course, you can slice this in different ways, but one good way is to think about it as predictive analytics, real-time analytics, and then descriptive analytics. But in this episode, I'd like to have you speak to predictive analytics. And so why don't we start with a definition? What is predictive analytics?
Yeah, so in some ways, the name itself suggests the definition. Mm-hmm. We want to predict something. So the question would be, why do you want to predict, or what's the need? What's the business need to predict something, right? So, as I alluded to that in the opening, in the automotive sector and in medical devices, for instance, mm-hmm. Prediction is important because you want to predict field failure. Right. So that's the metric, field failure.
Field failure meaning just something in the field that fails. Is that what you mean?
Yeah. So let me actually refine it or qualify it a little bit more. Product field failure.
Okay.
So the companies don't want their products to be failing in the field.
Right.
And if it has to fail, they would rather have it fail before it ships, even though they manufactured it, but before it ships. Because, as I mentioned earlier, the cost of discovering failures in the field is quite high.
Now, wouldn't you want to back that up even further and analyze it before you make it? So yes. More do the analytics in advance of making it, in advance of shipping it?
Yes. So actually, this whole concept of predictive analytics, it can be looked upon as a chain, actually. So all the way, and by chain I mean you can apply it all through the product life cycle.
Right.
In other words, all the way from design to prototype to high volume manufacturing and then post ship. So at all of these stages, you can apply these methods. The kind of data that is available at various points in the life cycle is different. So the methods you will apply would be somewhat different. Mm-hmm. But definitely, surely you can apply it right at the design stage. In the design stage, you're typically looking at similar products that you may have manufactured before.
Okay.
Right. So there's, so it's not going to be for this product because there isn't data for this product at that point. Mm-hmm. And there are other things that you can use, other methods that are based on anomaly detection and so forth that you can employ there as well.
So, yeah, let's talk about this a little bit in the design phase. So as part of the design phase, you're going to be building a product model. And could you not exercise that model to see how it reacts to generate the data and then use that from a predictive point of view based on past products? Or is that just too far out there?
You do, and that's precisely what I was mentioning also, or at least alluding to it. Mm. You take a look at data from past products that are similar. Now, obviously, this is a new product, so it has new things in it, or else It wouldn't be new. But that said, there are lots of things that are common to what you've seen in the past. So you want to be able to leverage that. And so what you're typically doing is projecting some of the models that you had in the past under the new conditions that you find yourself in. So you're taking a model built historically with a subset of data that you have now, subset of the variables, because you have more variables now or different variables. Yep. But the conditions in which you're applying may be different. And so you apply an earlier model to a new set of conditions, right? So, yeah. Mm-hmm.
No, so I was going to say, well, can you make this a little bit more concrete for our listeners and maybe use an automotive or a medical, I guess, use case or example?
Yeah. So, in typically, let's say in automotive, you're coming up with new SKUs all the time. And by SKUs meaning product IDs, for lack of a better description. And so you may come up with let's say you have a board that has a particular communication protocol. Then you have another version of it that comes out, hey, we want to add another protocol to it. So they add another chip to it.
Okay.
Right? And so now if you add something more to it, you have additional tests to test it. But the primary functionality that you had in the previous version is still the same, but you added a lot more things. Maybe you have a USB port or an Ethernet port, this or that, all kinds of stuff. And so you can still apply under those constrained circumstances a previous model to the new one. You won't be able to test for everything, but you still can test a lot of stuff.
Okay. All right. And so in the design phase, so throughout the life cycle, you could do prediction based on, again, like you said, you're going to have different data available, but in the design phase, in the in the manufacturing phase, and then I guess in the shipping phase as well. So your focus, I think, from the sounds of it, is earlier stage, or are you also doing or helping your clients with the analytics once the product has been shipped?
Actually, we do all of that, but I would our work is mostly in high volume manufacturing.
Yep.
And so because that is when you see these defects realized, actually. That's the first opportunity you have to detect them. And then we can get into various ways in which we can detect them, right? So, and in particular, let me bring up two ways in which we can do that at a very high level.
Okay.
And so, supervised learning and unsupervised learning. There's two words that I'm going to throw out.
Okay.
So supervised learning is very similar to what we were talking about in the last couple of minutes. It is based on a model like y is equal to fx. So y is your output, something that you're trying to predict, right? So you're trying to predict field failure, you're trying to predict a yield, or maybe you're trying to predict the performance of something. Yeah. So that's your y. So y is equal to fx. So that's, and of course we've done that for quite a long time, these kind of models. There's nothing particularly new in stating this because this has been around since the time of Gauss, early 1800s, if you like.
Sure.
And so people do regression models and all of that, right? That's what they build.
Yep.
So next time when you see a different X, you get a different Y. So there's nothing particularly unique about that. So, and so when we say supervised learning, is it just the same thing what we've done for the last 200 years, 150 years? Well, not quite. So the word that I'm going to use is machine learning model. So now in supervised learning, we have employed now a more advanced method of discovering this model.
Okay.
And so why do we even need that advanced method, you might ask? Well, the reason you need these advanced methods for discovering models is because techniques like regression, simple regression, they, as I mentioned, they go back a number of years, a lot of years.
Sure.
And at that time, people were collecting data by hand. So you had a small number of records, or small number of rows, if you like, small number of data points, and a small number of variables. So you had a small data set to work with. And this was true until recently.
Yeah, right.
And so now when you're looking at sensors, as I mentioned, if you look at semiconductor tools, for instance, there's huge number of sensors in a tool. If you look at an airplane, it is filled with sensors everywhere. An oil rig. So all of these places, if you look at, the amount of data volume is huge. So the implication of that is there's a mathematical implication, which is that those models that we had used for all this time, they have run up against its limits. And there's lots of mathematical reasons for that. There's some technical words that I can throw, which is one of them is curse of dimensionality. which means that you have too many dimensions, you have too many variables.
That's going to be too big of an equation there.
Yes, precisely. You got it. So you have too long an equation, too big an equation. So you might say, well, okay, so you have a big equation, you fit all the coefficients. What's the big deal? You have massive computers, and by massive not in size, but massive capability. And so it shouldn't be that difficult, and that would be true. It's not so much the compute power, because we have the computational power to do that, but there are some fundamental reasons why if you try to fit all of these things, it just won't work.
Okay.
And so you will end up with coefficients that are essentially useless or have no confidence. And so you would not be able to discover these things. And the simplest way to describe that is, if you have 10 unknowns, if you go back to your high school algebra, if you have 10 unknowns, you need at least 10 points, right?
Exactly.
So if you have, let's say, 800 variables, and you're looking for interactions, which I haven't addressed yet, many of these things interact with each other. Many of these variables interact with each other quite violently sometimes. And three-way interactions are totally not uncommon in the manufacturing, and which is to say they're common. So if you have 800 variables, and if you're looking at 3 variables at a time, 800 choose 3 is about, give or take, around 85 million. That means you're going to have to fit that many coefficients. So if you have that many coefficients to fit, not to mention the two-way interactions and linear terms, you need that many points.
Right.
You don't have that many points.
No.
And not even close. And so that means you have to have a way of finding which coefficients are important without having to compute all of them and then finding out which ones are significant. So the brute force way would be to compute everything, see which one is significant. We don't have the luxury of doing that because we don't have the number of points. So that means we need an optimal way to discover the important ones without having to do that. And that's where machine learning models come in. They're a highly optimized way of discovering the signal without doing this brute force computation of everything.
So the machine learning is still part of the supervised learning, you're saying. It's just basically cutting down the number of variables and therefore number of instances to solve those variables in the equations. Is that right?
Yes, perfectly put. So you're essentially trying to do a y is equal to fx, and the fx
to x order, or whatever order.
Exactly.
Yeah.
And the x is a highly nonlinear equation typically, lots of interactions and things of that nature. And usually a handful of variables. So you may start with, a lot of variables, like thousands or tens of thousands of variables. You'll typically, in a typical case, you'll be left with a handful, 6 or 10 or something.
Right.
And so to be able to arrive at that is tricky, and that's where machine learning models help. So you're right. That is part of the supervised learning model.
Okay.
Yeah. That's one aspect of it. As I mentioned, the other side is unsupervised learning.
And what would that be then?
Right. So speaking of that, so unsupervised learning is, again, as the name probably suggests, there is no supervising signal, which is to say there's no Y, which is also to say you don't have a historical data that you can model on which to say something about this current data.
Right.
So you have a streaming set of data, and now what you're going to do in this case is essentially detect anomalies. So you want to find out units that are different from the rest. And so the going assumption here would be that if a unit is different from the rest, there's something wrong with it because and this has been seen in practice many, many times in automotive. Things that are different from the rest of the population, they usually end up having a problem later on.
Okay. Yeah.
And there's reasons for it. And the simple reason...
They just don't fit in.
Yeah, there's a simple reason for it, actually, because when you detect anomalies, and I'll define what anomaly means here technically in this case, but when you detect an anomaly, just understand for a second anomaly in a colloquial sense, in an English language sense, meaning something that's different. And the reason something is different is because actually, let me put it another way. Anomaly in this case is a proxy for marginality. They're marginal parts.
Okay.
So, and I think I mentioned that right at the outset.
But what is the marginality again, or what is that again?
Yeah. So a marginal part is one that is going to pass every specification that you might have individually. But, and therefore you are going to ship it more typically. But it is marginal because many of these variables or tests, if you like, they collectively together create a picture that suggests that there's something different about this.
Okay.
So a marginality or an anomaly is a multivariate, another term which means multiple variables together.
Sure. Mm-hmm.
Multiple variables, when they're looked at together, this unit looks different from the rest. But if you looked at each unit, each test, I should say, for this unit, it may look very similar to the rest of the population.
Right.
And so therefore, the default would be to pass this unit and ship it. And so you see, if it fails an individual specification, you're not going to ship it, right? So that's not a problem from a field failure perspective because you caught it. So for problems that are severe, that would be the case. Some test would fail and you would not ship it. I mean, it's not good for the company. You'd have low yield, but at least it didn't end up in the field, right?
Right.
But the problem is when things are at the edges of the distribution. So if you consider like a normal distribution, and so one particular test could be at the edge of the distribution, right? At the edge of the distribution. And you have another test that is at the edge of another test that is also at the edge of the distribution.
Right.
So
you'll find it.
Right. So, and going back to design now, which is connected with this, when people design parts, they typically design parts with guard bands. They expect some manufacturing tolerance. They expect things not to be perfectly centered. So they design things so that you can tolerate some variation, manufacturing variation. And that's by design. It's true in semiconductor, electronics, mechanical systems, what have you, everywhere. So there's tolerance. Manufacturing tolerance is by design. So, but the point though here is that if you most of these units when you take collectively together, or most of these tests when you look at them together, they can tolerate variations in each of these tests individually. If one thing moved to the edge of the distribution, you're okay. If it's 3 sigma or 4 sigma. But if many of these variables are sitting at the edges or beyond that, like 4 sigma, then you have a problem. So they might still be within 6 sigma, which is near your specification limit or under your specification limit, meaning you're still within specification. But now you've reached the edges of many things together, and that's the keyword, together. And so that makes it marginal. So you have many things at the edges of their distributions at the same time, and you haven't designed for that.
Right, and that's a problem.
That's a problem. Because when you design, you say, well, this thickness can be between this and this, and then this torque can be between this and this. But however, when your thickness is at the edge of the distribution and your torque is at this other end, then you may have a problem.
Yeah. No, I get it. No, that makes a lot of sense. And just to tie the bow on this, then, what we were talking about in terms of supervised learning and unsupervised learning was effectively building that model that we use to determine or to find these anomalies for predictive analytics. Is that a good way of kind of wrapping it up?
Yes, correct.
Yes.
So unsupervised meaning you don't have a why, as I mentioned, right?
No.
So you don't have the facility of modeling based on historical data. This failed, and therefore I'm building this model. Y is equal to fx. Well, I only have x. So
you're fitting things then.
You're fitting. So
right? You're fitting things rather than solving things.
Yeah, exactly.
Is that right?
Yeah. So I'm trying to detect if this particular unit, in a multivariate sense, is distant from the rest of the population. That's basically what I'm doing.
Yes, and what you're saying, there's generally there's two ways. There's two technical ways to do that in the underlying, and you're saying again that supervised versus unsupervised learning.
Yeah. So in supervised learning, you're essentially building a model, and then the way you apply it is by discovering exclusion zones, right? Exclusion zone meaning this is the set of conditions you don't want to operate in. In anomaly detection, you're saying this unit is different, don't ship it.
Got it. All right, let's pop up a bit. I dig it. I'm hoping our listeners like to go down as deep as that, but I certainly do. But let's pop up a little bit, and I'm going to give you an easy one. But contrast that then to, we started with real-time, predictive, and descriptive analytics. Contrast predictive analytics, just at a high level, to real-time analytics and descriptive analytics.
Yeah, so descriptive analytics, or another word would be explanatory models, but descriptive analytics would be, think of it as looking backwards. So which is to say, you're trying to answer the question, what happened?
Right.
As opposed to predictive analytics, in which you're answering the question, what will happen?
Mm-hmm.
And real time, I guess, in some sense would be what is happening now.
Yeah.
And so you're trying to answer many times. Let's say you have a part failure or some other problem that occurred, device performance issue. At that point, your goal is simply to go back and look at historical data and model it. So explain why is it behaving this way. Right? And so the way it is different, descriptive analytics or explanatory models are different from predictive, is only in the way, only in terms of, well, I shouldn't say only. They are different in terms of end goal, but the way mathematically it gets manifested in the process is that in predictive models, you tend to incorporate or include a lot more variables. And in explanatory models, you include less variables. And while that by itself doesn't tell you much, but the more important thing in that is that in explanatory model, the models have to have a physical significance typically. Because the keyword there is explain. You're trying to explain why did this happen. You need a physics basis for it. Yeah. So you're trying to explain is this part, is this the short that is happening here? This part is shorting every now and then because you have lower thickness of a thin film here, or something else, right? So you're trying to answer a very direct causal connection there. And so typically you're going to bring in physics-based models, domain specialists who know the physics of the process or the chemistry or biology of it, as the case might be. So you're going to bring in those experts. So you're trying to explain, and you're only going to retain those variables that explain it physically. So you'll start with the mathematical model first, the supervised type of approach. You're going to reduce the number of variables and build models with various techniques. And end up with a model that can be physically explained. That is not the case in predictive, because in predictive, let's say you're in high volume manufacturing and you're trying to predict, let's say in real time or in near real time too. At that point, you're trying to make a prediction. Is this part going to fail in the field? For instance, that may be one of the goals, let's say. At that point, at the decision level, the part just came out of some manufacturing process step. You're trying to make a decision based on the data you have, the IoT data that you just collected from the tool and probably some other data. I'm trying to make a prediction, is this part going to fail? At that point in time, when you're trying to make the decision, it's not important to know why it's going to fail. And therefore, the focus in the explanatory model, which was to explain it physically, that focus is not there. But now the focus is you have to have much greater degree of confidence in the conclusion that it is going to fail.
You know that though, right?
Yes. In the explanatory model, that was not the focus. By paring down the variables, you actually reduced your accuracy in the sense, but you were left with those variables that you could explain. And so that's why I mentioned in predictive models, typically you might have more number of variables that help you predict better, but you don't really know why they're there on a physical basis.
Right.
So that is sort of the primary difference between the two.
Yeah, no, I like that. So what you're saying is, yeah, the difference being in descriptive, you're trying to describe it in some way, and describing it is going to be one good way to do it is with physics equations or chemical equations or biological equations, and then you can use that and, as you said, find a causal purpose for what happened or whatever happened. However, in predictive, you're just trying to predict things, and it's not really anything. It's not necessarily to an end result. You're just predicting something based on other data. But getting back on the descriptive, there's also a part of descriptive analytics. Where does visualization fit in? Where you're actually using the human brain as opposed to the algorithms, to describe what's happening or to, I guess, recognize what's happening. I mean, how does that fit in?
Yeah. So, visualization, of course, is a new focus on that, because if you look back, say 25 years ago, I think the engineering mindset at the time was that if you had a table, that was sufficient. Mm-hmm. And even today, in some circles, you can identify who is an engineer and who is not an engineer by their preference for pie charts versus other charts.
Okay.
Right. So if you wear a suit, you're more likely to like a pie chart. If you wear t-shirts, you're likely to enjoy scatter plots.
Right.
So the visualization portion of it, that's sort of the historical context. But more recently, even on the engineering side, there's a greater realization that visualization is very important in terms of making decisions, because your solutions are in the hands of non-engineers many times. It may be in the hands of an operator who's making the decision right there. And some of the things have to stand out so easily that it should not need an explanation. So visualization is very important. And so if you look at predictive analytics, for instance, I'll take the example of that, and then also likewise it applies in descriptive, but in a different way. The focus of in predictive is that, as I mentioned, it has to be obvious to everybody, because you're making split-second decisions. Am I going to ship this part or not?
Okay.
Right? And many times, especially in near-time systems, near real-time, not so much in real-time, but the near real-time and not so real-time systems, there's typically a human involved in the loop to make that decision. Mm-hmm. And because of that, visualization is very important, because you have to allow them to be able to do that slicing, dicing, and see the impact so easily that they can make that split-second decision. In explanatory, the purpose is very different, because now it's a drill down, right? So it's a drill down. So the more you can drill down, the better. So
right.
So I mean, all the different dashboarding platforms, they're all good in that. So take the handful of ones that everybody's familiar with. They all do a very good job these days.
Yeah, and I think for our listeners, we need to set the context. I mean, in your context, you're looking at it in a manufacturing context and almost a near real-time context, and so. Yeah, I mean, the visualization of it is going to be used in this purpose. However, if you had a little bit more luxury of time, like you were saying, one is to describe it physically, but another way is if you had a bit more luxury of time, you can let a person kind of look at the data, whether it's a scatter chart or a multi-dimensional version of a scatter chart, and play around with it to kind of make up or to kind of deduce what happened if you can't necessarily figure it out with algorithms, right?
Yes. I think so. I think visualization is becoming important. I think that's the best way to.
I think it's becoming important, and I think, my view anyway is that, like you said, I mean, there's kind of two approaches. I mean, one approach is to try to fit a model to the data and then have a causal effect, and whether it's a physical effect or a biological effect or a chemical effect, just like you said, if you can figure out what the equation is to each of those, disciplines, then you can identify a problem. However, sometimes you may not be able to do that, and a visualization may be a way of presenting the data to a person, and the brain sometimes just works in very different ways, and it can pick up, things that you can't necessarily deduce analytically,
Yeah, I'll put very simply, over the last 10 minutes, I was mentioning about the multivariate nature of these things, right? Things interact with each other. Things stand, and multiple things are at the edges of their distributions. Things tend to go haywire because they produce marginal parts, even though they're passing individually. So how are you going to visualize these multidimensional things, right? I mean, that's the key here. So the reason you need visualization in these areas, particularly the ones I deal with, is because you have multidimensional effects.
Right.
And so, now 3D charts have been around for a long time, but if you've seen any 3D chart, you're trying to, move it left and right, it's not particularly, not particularly descriptive in some sense, unless you interact with it. So if you just have a flat chart and
Sure.
put it in a PowerPoint, where you don't have the luxury of rotating the chart left and right or up and down, you will
or changing the variables even. I mean,
and that's why you have these new ways of depicting multiple dimensions in one flat chart.
Right.
And that's the key advance in visualization that I think is necessary for these kinds of analytics.
Interesting. Okay, and then the other thing I like is what you said, and I agree, is looking at predictive versus real time versus descriptive is the dimension of time. And we know that there's going to be overlaps, but I like, the concept of real time being, well, you're looking at what's happening now, and predictive, you're looking at what's going to happen in the future, and descriptive, you're looking at what's happened in the past. But we know that there's overlap, obviously, in the different techniques, because there may be some predictive with descriptive. There may be some descriptive with real time, and so forth and so forth. But I think that's probably a good mental kind of framework to think about it as well. Can you think of any other ways, or is that kind of a way to leave it?
Yeah. So maybe one thing. Yeah, that's correct. I agree with that actually. But I would only add that if you one way to think in the real time, you could ask the question, so why do you need real time versus non-real time versus not so real time at all?
Yeah,
so, you're trying to predict in all of these cases, but there are pros and cons and pluses and minuses. And so the real time, if you're trying to predict something in real time, the advantage is sort of obvious. Because if you predict right now this part is going to fail, you stop it right now. So you're not processing the part. You're not wasting energy processing the part to the next few steps, right? Why are you going to make that effort? On the flip side, real-time systems require connectivity to MES, or manufacturing execution system, or a shop floor factory control system. And when you do that, the onus on the software is significantly higher than not connecting with these systems, because these are mission critical systems, MES and so forth. Anytime you touch anything to do with the MES, any data interchange, this or that, it goes through an entire level of certification and all kinds of stuff. So an easier way to do that is that these systems push the data out to some known place, and the compute systems, the predictive systems, they absorb that, make a prediction, and typically there's a human involved in that. They can take a look at the data. They can either override it, buy it, and then instruct the system to do something about it. So there's the advantage that you don't have to touch the MES. There's the disadvantage that you're processing in the part for some more steps before you actually discover it, perhaps. And there might be a human involved in the loop, which means it's more resource intensive. So there's trade-offs in that. Real time typically also would be you need to be computing fast because you're making the decision right now. Typically you use less data, which means your analyses have to be in some ways more complex. And by complex, I mean they're more complex in the sense they have to be able to infer things with less data. Right.
And so the pre-processing of that model, for example, is maybe a little bit more sophisticated so that you can work on it with less data so you can do it in quicker time.
Yeah, so they can afford less compute time. So the trade-offs are they lean towards computing things fast as opposed to the most accurate. When you have the luxury of more time, you will compute longer because it's a nonlinear trade-off typically in accuracy versus time. At some point, you need much more time to get a little more accuracy.
The 80-20 rule almost.
Yeah. So when you're doing real time, then you make that trade-off with less accuracy, but less time.
That makes sense. And again, for our listeners, the context here is describing it in a manufacturing kind of assembly or a manufacturing plant situation. But of course, you could project this into many other real-time situations where what you're checking is not whether or not there's a defect or a flaw in the part, but whether or not the part that's in the field is going to overheat or it's going to break or it's going to do something that it's going to act. There's going to be an anomaly in the way that it's going to act.
Yeah,
right?
And actually the one application where real time has to be real time is with respect to medical systems that people are wearing on their bodies. And I don't mean just wearables, but other medical systems. Wearables would be like a more consumer version of wearables.
Sure.
But also those that are medically necessary type of systems. Pacemakers on steroids, if you like. So all kinds of new things are coming up in that space. And so you're collecting lots of information. But those decisions sometimes may need to be made like yesterday, like really real time.
Right.
And so there, the importance of real time becomes magnified. And I think that's where we're headed.
Yeah, but as you said, which is I guess it's kind of the issue is that the more real time it has to be, the more or the less data that you can use to process it. And so if real time becomes really important, that means you're making really important decisions on less information. So how do you get around that? I mean, what are the tricks to get around that problem?
Tricks to get around which problem? I'm sorry?
Well, effectively what you're saying is that to do it in real time, you need to have a less sophisticated model, let's say, or you need to be solving less things. However, if you're solving less things, that implies less information, so maybe not as accurate of a model or of a prediction, for example. So if you're having to do something real time, like let's say a medical application, yet you don't have the computational resources to ingest loads and loads of information to make a really good decision, what do you do? I mean, what are the trade-offs that are made then?
I think in those situations, and this is true in manufacturing as well, but it's going to be even more true in that scenario, medical scenario, is that you're going to want a confirmatory signal post that decision. So,
okay, what does that mean?
Which means that you will make a decision right now, let's say, let's say the case of manufacturing, and similar case would be for medical. Let's say you decide to hold this part because you're predicting it to fail. But that's not the end of the story. You may do some further analysis on it. You may discover, well, that's not really true in this case, and I'm going to ship it. So you might actually add back to the production line. And so it may fail your confirmatory test later on. And so hopefully that is not the case, meaning your initial prediction is correct and it will stand the test of confirmation. But occasionally it will be the case that it may not. This is the cost of accuracy. This is the trade-off that you would have made. That occasionally, once in a million, you may take, or once in 10,000, whatever the one in something is. So one in X number of times, you will have a false positive. And the way to recover from that would be a confirmatory test. And so you are not going to rely entirely on that signal. It allows you to take some quick action, but you're not going to take drastic action. You're not going to shut down the line, for instance. Okay. Just holding the unit, sending it for testing. In the case of medical systems, you may be triggered to go see someone, but it doesn't mean you're going to go into surgery.
Right. So okay, yeah. So I was going to say, so then you're going to take that data and then use it to improve your model for next time around?
Yeah, it will, correct. So which is the learning in the supervised learning. It's the model will build on itself because now you have one more data point in your number of records that suggests that if this happens, if this condition is true, then that happens. Right. That's what learning is.
Okay. Well, Anil, I think this has been a fun deep dive for me. Where can people find out more about you and more about your company and what your company does? Sure.
So they can look us up on the web at Qualicent.net, and I'll spell that. It's QUALICENT.net, and they can email me too, which is first name dot last name ANIL.GANDHI@Qualicent.net.
Oh, excellent. Well, Neil, I'll put both those pieces of information in the show analysis notes. So for anyone listening, if you're driving or walking the dog or whatever you may be doing, just come to the show analysis notes and the information will be there. And check out Qualicent, what they're doing. And thanks a lot for the education on predictive analytics.
Sure, you're welcome, and nice talking with you, Bruce.
Okay, well, that was episode 26. For summary and links and other valuable resources, like usual, go to the show analysis notes. They can be found at iotinc.com/podcasts. Now remember, with IoT Inc., there is that hyphen between the IoT and the Inc. Well, now I could use your help. We're trying to get this show off the ground, and the best way to get discovered is with iTunes. So if you've enjoyed the episode or found it informative, I'd really appreciate a review. All you have to do is go to iot-inc.com/iTunes, and that'll redirect you to our iTunes page where you can let people know what you think by simply giving this show a star review or leaving a comment. I'd really appreciate that. If you'd like to learn more about the business of the Internet of Things, visit my media site. It can be found at iot-inc.com. There you'll find other podcasts as well as articles, videos, and information about upcoming live events like my stream meetups and webinars. Now, as always, you can send me an email if you have any suggestions on how I can improve this show. My email address is bruce@iotinc.com. I'd love to hear from you. Now, it's something I've been doing more and more, and if you're interested in making connections with other people in my audience and also all my guests, send me a LinkedIn request. I'd be happy to connect you to someone in my network whenever it makes sense. I'm your host, Bruce Sinclair. Thank you for listening. And until next time, may your path to IoT business be a modeled one.
You have been listening to the IoT Inc. Business Show.